Okay, we gave this argument when we looked at the harmonic series. We gave this area argument to show that it diverged, right? So if we looked at the sum n equals 1 to infinity of 1 over n, we said, okay, we can visualize that sum if we sort of plot the values of the summands, the 1, a half, a third, a quarter, a fifth, and so on. We said, okay, we can plot these etc. That's at height 1, that's at height a half, not to scale. We said, okay, let's look at these values. And we are going to interpret that as an area, but before I do that, let me just draw the curve through this. And we said, okay, well, we actually have this curve, y equals 1 over x. And we have this area, which is the integral of 1 over x from 1 to infinity. So we're going to keep going forever to the right. And we said this diverges. So this area, we know that from previous considerations. So the area under this curve is infinite. And then we drew these rectangles. So this is a rectangle right there, like that. These are all rectangles. And, this has area 1, this has area half, because the width of each rectangle is 1, right? And the heights are 1, a half, a third, and so on. And so we said, well, the area inside the rectangles is greater than the area under the curve, but the area under the curve diverges. Therefore, the area inside the rectangles also must diverge. So let me just write that. We saw this in the harmonic series. I'm just recapitulating the example just to show us that I want to see how this is going to generalize. So the area under the rectangles is greater than the area under the curve, which is already infinite. And so if you're greater than something that's infinite, you are also infinite. You are all infinite. We are all infinite. And this is the sum equals that area. And so this diverges, this sum diverges. Okay. So I want to do the same thing, but for some different examples. So I guess up here, this was one example, harmonic series example. Let's do another example. So let's look the sum of 1 over n squared, which is kind of a famous series in its own right. It has some interesting, shows up in interesting places in mathematics, but which maybe I'll say something about in a moment. But so if I look at the sum of 1 over n squared from 1 to infinity, so that's just 1 plus a quarter, plus a ninth, plus a 16th, plus a 25th, and so on. We're just summing 1 over the perfect squares. And I'd like to know whether this converges or diverges, right? So again, we can sort of plot this, we can visualize this sum as an area. So the picture is going to be very similar to the picture up at the top here. So visualize as an area again. And the only difference is that the rectangles, I guess, the height will go down more quickly, which is going to be hard to see in the picture, but I can't really draw a picture that carefully without losing something. But let's, I mean, it'll look fairly similar to the other picture qualitatively. But let me just think about this. Let's put the height one up here. So if I start plotting these, it's one, now the next one's a quarter, and the next one's a ninth. So this actually dies very quickly. Maybe I'm giving you some sense of that it dies much more quickly. So those are the heights. Those are the terms, one, a quarter, an eighth, the ninth, the 16th, and so on. If I again draw the curve, before I draw rectangles, I actually want to draw the curve, just because we know what happens to the area under the curve, right? So this was one of our famous examples where the area underneath was finite, it actually converged, right? So if we look at this area, this is the very first improper integral we actually looked at. So the area integral from 1 to infinity of 1 over x squared dx converges. We actually showed that before, as opposed to the integral of 1 over x, which diverged. And now, okay, so that means the area under the curve is finite. And so we would like, so I claim that the sum of 1 over n squared is also finite. But that means I don't want to draw a rectangle like this. If I draw rectangles like this, then these are overestimates, right? And so we get something that's bigger. If we did this, we would get something, again, that was bigger than the integral, which would mean, but it's bigger than something finite, which means it could be just a bigger finite number, or it could be infinite. And so that doesn't tell us anything. So I don't want to do this. So I'm going to back up. I'm going to erase. So, okay. But I'll show you a fix here. You can actually make the rectangles be underneath the curve. If you just do this, this is a rectangle, and this is a rectangle, and this is a rectangle. And you might think, and the rectangles get small, but you can sort of see. Right? Now, the problem is that the first rectangle has height 1/4. So the area under these rectangles is actually a quarter plus a ninth plus a 16th plus a 1 over 25 plus so on. So that's actually the sum from n equals 2 to infinity of 1 over n squared. But we just showed, just from this picture, we can see that's less than the integral from 1 to infinity of 1 over x squared dx. By the way, an aside here, for some reason, we tend to use x for like any real number, just a choice of letters here, and n for counting numbers, for whole numbers, for integers. So that's why that's one reason I switched from n to x. And it's good to keep the sort of series and the integral separate conceptually, so it's not a bad idea to switch the variable. But anyways, this is just sort of a thing that's a convention in math that people tend to use. You know, you say to the nth degree or something, it doesn't mean like the 5.2th degree. It's usually n means a whole number. Okay, so anyways, that was indecide. Back to the main argument that this is this integral was finite, and this is less than it. It's also greater than 0, so it's bounded between two finite numbers, so this is also finite. Right? Now, but this isn't the exact same series we had. This series starts at 2, whereas the series that we started with starts at n equals 1. But does that really matter for convergence? The only difference is, if you think about it, what's the difference between the sum from n equals 1 to infinity of 1 over n squared? That's really 1 over 1 squared plus the sum from n equals 2 to infinity, right? It's just stripping off that first term. And so if we know that this converges, which we just gave an argument, this area argument to show, then of course, if you add 1, this also converges. Right? It doesn't change whether the value is finite or infinite just by adding 1. And that's the general principle, that convergence all happens in the tails, that it really doesn't matter. I could strip off the first million terms of the series and it wouldn't affect whether that's some finite sum. It wouldn't affect whether the total sum is going to infinity or not. So it doesn't really matter where you start in terms of the question of divergence or convergence. You can start with n equals 1, you can start with n equals 2, you can start with n equals 1,000. If it's the same series, 1 over n squared, they're all going to converge. And so this is an argument that the sum of 1 over n squared converges. Okay. And so in general, but notice this, the whole idea was to compare to the improper integral. And so just recall that we have the p-test for the improper integral, we called the p-test. The integral from 1 to infinity, 1 over x to the pth power, that there are 2 possibilities, right? This converges if p is greater than 1, and it diverges if p is less than or equal to 1. And so that's something we showed with improper integrals. This is sort of the avatar for an improper integral that could possibly converge, because you need the function to be going to 0, and as the function, as x goes to infinity, as the input goes to infinity. So this we called the p-test. But what I'm showing, what these 2 examples for 1 over n and 1 over n squared, those series shows, is that you can show that the area sort of also does the same, the area in the rectangles is the same thing as the area under the curves, right? Like in the top, we made the rectangles bigger in this top picture. We made the rectangles bigger than the area because the area was infinite. So we wanted to show that the rectangles, area under the curve is infinite. So we wanted to show the area inside the rectangles, which is the infinite series, is also infinite. Whereas down here, we had a finite area under the curve. So we wanted to make something smaller, right? We wanted a smaller area in the boxes to show that that's also finite. And this generalizes. So the arguments for 1 over n, 1 over n squared generalize. And I won't even probably go through the details, but you can sort of see that if we had 1 over root n or 1 over n cubed or something, these generalize to sum of 1 over n to the p for any positive power p. I guess p is greater than 0 here. I mean, it's true actually that it would diverge if p was like negative, that the integral would diverge if p is negative. But the point is like, if we just want to sort of think about this generalizes to the sum of 1 over n to the p. And because like I said, if you did 1 over n to the 4th, you would just do the exact same picture that you drew for 1 over n squared. And that would, because the integral of 1 over n to the 4th converges, so the series would also. But if you wanted to do 1 over n to the 1/2, p equals 1/2, you would draw the same picture as you draw for p equals 1. So yeah, for p less than or equal to 1, draw the same picture as for p equals 1. And for p greater than 1, draw the same picture. And you have to do that one little extra piece of the argument where you start at n equals 2 instead, but that doesn't affect the convergence starting at n equals 1 or starting at n equals 2. And so this gives us a p-test for series, just like we had a p-test for integrals. P-test for series says that the sum from n equals 1 to infinity, although it could be n equals any finite number to infinity, of 1 over n to the p exactly the same as for improper integrals. It converges for p greater than 1, and it diverges for p less than or equal to 1. And that's the p-test. Again, I want to just mention that this is kind of shows the subtlety that in all these cases, if p is greater than 0, in all these cases, the limit as n goes to infinity of 1 over n to the p is 0. Write those a little better. That limit's 0, but that doesn't always mean that the series converges, right? That was my point at the end of the harmonic series video, that knowing the terms go to 0 is not enough to show that a series converges. If the terms don't go to 0, the test for divergence says that the series must diverge, but the terms going to 0 is not enough to say that the series must converge. In fact, something like 1 over n, 1 over root n, individual terms are getting smaller and smaller, but the sum still diverges. 1 over n squared, 1 over n cubed, 1 over the fourth, the sum. Terms are going to 0, but they're going to 0 faster, and somehow they're going to 0 fast enough that the series actually converges. That's kind of the thing that we saw up here, where the curve dies off more rapidly, and so the area is actually smaller, and it ends up being small enough to converge. Although that's not really intuitive, it's just what the math tells us. Okay, so that's the p-series. We'll generalize this in a moment to integral test. That'll be the next video.